Hi there, and thank you for joining us for our next video in this Integrated Math 1 video series. We're going to get into solving systems of linear inequalities today. But before we do that, let's go ahead and do our 4 warm-up problems for today. So take a second and do those. Alright, so in number 1 there, we're going to come back to this one and look at the graphs of these, because that's really going to help us get into what we're going to do today. Let's go ahead and do number 2 first, and then kind of work our way from there. So in this one, we've got 6x minus 1 is less than or equal to 7x plus 9. Really, you're going to solve this just like any other linear equation, only if you divide or multiply by a negative number, you're going to have to switch the sign. And we talked about why that was a few videos ago. So in this case, let's go ahead and solve for x here. So I'm going to subtract 6x on both sides. So it's going to give us negative 1 is less than or equal to 7x minus 6x is just x plus 9. And then let's see, to get x by itself, we're going to subtract 9 on both sides. So we're going to get negative 1 minus 9 is going to be negative 10. Notice we didn't multiply or divide by negative, we subtracted 9. So it's going to stay the same. So x is greater than or equal to negative 10. You could write it like that, or x is greater than or equal to negative 10 would be the same thing there. So any x value is greater than or equal to negative 10. So negative 10 would work, but also things greater than that like negative 2 or 0 or positive 7, anything like that would work as well. All right, in number 3 here, how many solutions does 5x minus 1 is less than 3 have? Well, if we solve for x here, we're going to get 5x is, let's see, if you add 1 to both sides, so we're going to get less than 4. So x is less than, divide by 5 on both sides. So we're going to get x is less than 4/5. How many numbers are there below 4/5? There's an infinite number of numbers, right? So inequalities actually give us a solution set or interval rather than a particular number value. Negative 2 would be a solution, negative 100, 0, and any of those would be solutions to that inequality. Number 4, increase 700 by 4%. So again, we're going to take the two numbers involved without any trailing zeros. So 4 times 7 is 28. So it's either going to be 28, 280, or could it even be 2.8 or 0.28? So let's make sense of this one, all right? So 280 is going to be way too much. 280 would be 40% because it's just under half of 700. So 280 would be 40% of 700. So therefore, yes, 4% is actually going to be 28. So we're going to increase it by 28. So it'd be 728. That was one way to do it. Or you could multiply 7 times, if we want to increase by 4%, that'd be multiplying by 1.04. So you can multiply 7 times 104 and then move the decimal a couple of places. And you would get the same thing there. All right, so going back to number 1, if you were to graph this inequality and this inequality on the same coordinate plane, let's take a look at what you should see there. So the blue one here is y is greater than or equal to negative x plus 2. So if we think about just the right side here, negative x plus 2, it's got a y-intercept of 2, which you can see there, and a slope of negative 1. So negative, or down 1 over 1, down 1 over 1, so on. And then it's not equal to, it's greater than or equal to. So the equal to here means the line is solid, meaning points on this line satisfy this inequality. So for example, the point 0, 2, or the point negative 2, 4. Those are solutions to this inequality as well. But it says greater than or equal to. So greater than means you're going to shade above the line. So pick any point and go up, and that's the region that we're wanting to shade. So the blue, that's why all of this is blue from all the way down here, all the way up there, and then extending forever in that direction. So greater than or equal to there. So any point in here is also a solution, or in here is also a solution to this inequality. For example, the point, this is 6, 0. If we put 6 in for x and 0 in for y, you're going to get negative 6 plus 2 is negative 4, and 0 in here. So 0 greater than or equal to negative 4? Yes. So that means that point is a solution. Okay. You've done that before, I believe. You've graphed linear inequalities before. But the main difference here with a system of linear inequalities, that's our goal for today, is to graph a system of linear inequalities. That just means you're graphing more than one on the same coordinate plane. All right, so we've graphed our blue one. Now we've got our red one down here. Y is less than 2x minus 3. So if we just look at the right side here, 2x minus 3, it's got a y-intercept of negative 3 right here, and a slope of 2. So up 2 over 1, up 2 over 1, up 2 over 1, and so on. So we've graphed it, and it says less than. So notice it doesn't say less than or equal to. And because of that, this line is dotted, okay? So that means that the points on the line itself are not solutions to that inequality. Just points below, all right, because it's less than, y is less than. So pick any point and go down, and that's the region that you're going to shade, okay? So we've got our blue is all the way up here, red starts up here and goes all the way down in here, and the key here is if we were to graph them on the same coordinate plane and look for the solution to this system of inequalities, now we're looking at where do they overlap, okay? So this region right here, this triangle looking region right here, that's just a solution to the red, right, to this inequality. The one that's solely blue up here, that's just a solution to this inequality. But where they overlap, this region here is a solution to both, and that's the solution to the system. So any point in here is a solution to this system because it's a solution to this one and this one at the same time. Okay, so point here, 4, 0, the point 4, 2, the point 6, 4, the point 8, negative 2, all of those are solutions to this system. So if we were to say solve this system of inequalities, y is greater than or equal to negative x plus 2, and y is less than 2x minus 3. All of these would be solutions. So really your answer is this graph. There's no way to write out every single solution to this system. And so what we do instead is we just graph the solutions this way. And so you can see on the coordinate plane all of the points that would be solutions. And so it's a little bit different than solving a system of linear equations, because then you're just looking for where they intersect, right? But now we're looking for where do their regions, their shaded regions, intersect. And so it's an infinite number of points that satisfy that, because of course we've got our decimal values and all kinds of different points that we could have in there. All right, so that's our goal for today. Really, we've already done the major work of it in terms of understanding how to graph these and finding their intersection. But there's some other things that we want to do as well and get into more detail and practice this a little bit. So I've got an example here. We've got a shaded region here. Y is greater than x over 2 minus 2. Is this point T a solution to this inequality? And the answer is no, right? Because this point right here is not in the shaded region. But also, let's check it. If we put 4 and negative 2 in, so negative 2 is the y value. So we're going to put negative 2 in for the y value and 4 in for the x. So we're going to get negative 2 is greater than 4 over 2 minus 2. So all I've done is put negative 2 in for the y value and 4 in for the x. So let's simplify this. Negative 2 is greater than 4 divided by 2 is 2, minus 2. So negative 2 is greater than, 2 minus 2 is 0. Is negative 2 greater than 0? No, right? Which makes sense because we knew it wasn't a solution in the first place because it wasn't part of the shaded region. All right, so just wanted to point that out there. Let's see here. And our next one, okay, so it says make it a solution. So if I drag this point and I put it into here, now it's a solution. So as long as it's part of that shaded region, it is a solution. Okay, this one. Right now, this is not a solution to the system. What about here? Is this one a solution to the system? It's not, right? Because this is a solution to one of the inequalities, but not both. All right, so how about this one? Is it a solution to the system? Yes, it is, right? Because it's part of, it's in the shaded region of both of our inequalities here. How about this one? Joseph moved the point to 2, 7. Is his point a solution? So is this point right here a solution? Because it's on the line. And the answer is yes, because this is a solid line, so it's still part of the blue in its shaded region. Okay, but what if we were to put the point here? What about there? Is that a solution to the system? No, it's not, right? Because it's in the blue, so we're good there, but it's on the dotted line of the red. Remember, the dotted means that's not part of the shaded region. So the line itself, any points on this line itself, is not in the red. So while that point's in the blue, it's not in the red, so therefore it's not a solution to the system of inequalities. All right, and then lastly here, let's just try this one real quick. Which of these correctly graphs this system of inequalities there? So try that one, see what you can do. All right, so let's see here. It looks like they all have the same lines involved, so we don't need to worry about checking the y-intercepts and slope, but let's figure out which one's which. So this has a y-intercept of -3, and this one has a y-intercept of 2. So it looks like the red line in each of these is the top one, because it intersects at -3. The blue one is the one that intersects at 2, okay? So let's see, -3 is the red one. So it says y is less than, so it should be graphing below this line. And notice it doesn't include, so we shouldn't have a solid line, we should have a dotted line. So below the red line, but dotted. Oh, here we go. This is below the line and dotted. And that's the only one that does that. So this one should be our answer. So that's how you can kind of check things, is figure out which one's which. And then look at the shading, look at the dotted or solid aspects of it, and then narrow down your choices from there. Okay, let's hop back into this and look at our next example here. This is actually a TN Ready type problem where it says, we got the system of inequalities, select all ordered pairs that are solutions to this system of inequalities. So there are a couple ways we could do this. One way is we can actually just substitute the values in. So let's check the first one here. So we're gonna put -10 in for the x values, and remember, it's gotta satisfy both. This point has to satisfy both inequalities. So for the first one, it'll be 3 times -10 plus 2 times -3 is less than 8. So again, I'm checking this point here in the first inequality up there. So it's gonna be -30 minus 6 is less than 8. And it's gonna be -36. Is -36 less than 8? Yes. Okay, so this one worked for the first one, but what about the second one? Let's do this in blue. -5 times -10 minus 9 times -3 is greater than -2. All right, so we have a +50 and a +27. And I don't even need to finish this here, right? I know that this is going to end up being more than -2. So this first one is a solution to this problem here in this system. Now, as you can see, this might take a little while to kind of go through each one of these. So maybe a different approach would be to graph the system of inequalities and then plot the points and see which points are in the overlap of the shaded regions. All right, so maybe we can take that approach instead. All right, so to graph these, we're going to need to solve for y and get y by itself. So in this first one, we're going to have, let's see if we, 3x plus 2y is less than 8. Let's solve for y. So if we subtract 3x from both sides, that's going to give us 2y is less than -3x plus 8. Let's divide by 2. So it's going to be y is less than -3/2 x plus 8 divided by 2 is 4. So again, we're dividing both terms by 2. It just so happens that 3 is not divisible by 2, but 8 is. All right, so if we think about this line here, it's got a y-intercept of 4 and a slope of -3/2. And we're going to shade below that line, and that line will be dotted. All right, and our bottom one here, do this in red. -5x minus 9y is greater than -2. We're going to add 5x to both sides and get -9y is greater than 5x minus 2. Now we're going to divide by -9 on both sides and get here, let's see, y is, careful here, we divided by a negative, so that means we're going to have to change the inequality from greater than to less than. -5/9 x minus, actually it's going to be plus 2/9. Okay, positive divided by negative is a negative, negative divided by negative is a positive. So those are our y-intercept and slope there. So if we were to go to graph these, okay, we could see it here. All right, again, one of those had a slope of 4 and y-intercept of 4 and a slope of -3/2. So down 1, 2, 3 over 1, 2. Okay, the other one had a y-intercept of 2/9, which is right here, and a slope of -5/9. So down 1, 2, 3, 4, 5 over 1, 2, 3, 4, 5, 6, 7, 8, 9. There. And then we can just plot the points and see which ones are solutions and which ones aren't. So we can very quickly visually see which ones are solutions and which ones aren't. So I'll do that here. So this one, 8, 9, is not. How about this one? -1, 5. That's barely inside this region. But is it in the blue region too? It's not, right? So this one's not a solution as well. How about this one here? It's on both lines, but both lines are dotted, so it's a solution of neither one. So 4, -2 is not a solution either. 0, 0 looks like it's in both shaded regions there. 1, -1, yes, and of course 10, -3, which this one we checked algebraically, didn't we? And we can see visually why that one is a solution as well. So we have 3 solutions, 0, 0, and 1, -1, and then the rest are not. So those are the 3 solutions there. All right, so one of the main reasons why I want to learn systems of linear inequalities is to apply it to real world situations. So in this case, we've got Sloan. She knits scarves and hats to sell at local craft fairs. It takes her 3 hours and 30 minutes to make a scarf and 5 hours and 15 minutes to make a hat. So let's talk about time. If we were to come up with an expression to represent the time it takes her to make scarves and hats, well, let's see. It takes her 3.5 hours, right? 3 hours and 30 minutes. That's 3.5 hours to make a scarf. I'm going to put that in S, okay? Plus, how long does it take her to make hats? Let's see, 5 hours, 15 minutes. 15 minutes is actually a fourth of an hour. So 5.25h. Okay? So this is time. Okay, then it says she uses $10 worth of yarn for a scarf and $4 worth of yarn for a hat. So if we talk about dollars or cost, $10 per scarf plus $4 per hat. So this expression represents how much time she takes given a certain number of scarves and hats, and this represents how much she spends to make S scarves and H hats. It says she wants to spend at most 140 hours knitting, at most. So this time, at most 140 hours. So can she spend 140 hours? Yes. But at most means she could spend less than 40 hours. So less than or equal to 140. And at most $200. So $200. So our cost needs to be less than or equal to $200. So we have these two inequalities here from this situation. All right, so I want you to take a minute and see if you can graph this, the solution to the system of inequalities. All right, so I would recommend, in this case, substituting x's and y's in here, because you're going to need one to be your independent and one to be your dependent variable here. If we go to the graph of this, we can see we have hats as our y, and scarves are our x, and we have dollars and hours. So our dollars is the blue, and our hours is the red. So hopefully you were able to, you could do the cover-up method and kind of find the y-intercept and x-intercept of both, and then go from there and connect the two. But anyways, we have this solution here. So everything in here is a solution to this inequality. But be careful, because we want to think about the situation here. If we go over here, we're talking about negative scarves. If we go down below the x-axis, we're talking about negative hats. We can't make negative of something. So if we were to think about the actual solution to this contextual situation, it would be this area right in here. This is the area we're talking about, okay? Because we don't. This is our hours, right? So if we made 30 scarves and 2 hats, that'll be that point right there, because we have a scale of 2 here. So 30 scarves and 2 hats, okay? That would satisfy the hours, or I'd be okay hour-wise, but I would be spending too much money because it's above the blue in that case. Whereas here, if I'm in here, maybe I don't know, 8 scarves and 24 hats. Well, I'm good dollar-wise. I've spent under my allotted amount, but I've spent too much time. Okay, but what satisfies both is all the ones in here. So let me just pick a point here, a few points. So this is the point 10, 10. So I can make 10 scarves and 10 hats. This is the point, let's see, 2, 4, 6, 14. I can make 6 scarves and 14 hats. Any point in here would satisfy our situation. So just kind of an interesting way to take some constraints, plot them on a graph, and find the points that actually satisfy our situation here. All right? All right, in our last situation here, we've got Karen, and she's hosting a baby shower. She wants to spend less than $250 and make up to 40 purchases. Each food item costs $4.50, and each party favor costs $9. Graph the solution set to describe the various number of party favors and food items she can buy. So take a few minutes, see if you can write the system of inequalities, and then graph the solution set. All right, so if we think about our two equations here, or inequalities, we're going to have one for cost and one for items purchased. okay? So for cost, each food item costs $4.50. So $4.50 F is the number of food items that we've purchased, plus 9 times the number of party favors we purchased. And we want that to be less than 250. Notice it didn't say up to 250, it said less than 250. All right, items. We've bought F, food items, P, party favors. So together that makes the total number of items we bought, which need to be less than or equal to 40, right? It says up to 40 purchases. So if we take F and make that X, and P and make that Y, we now have our system of linear inequalities that we can now graph. This first one down here is going to have a y-intercept of 40 and an x-intercept of 40. So it's going to be easy. Up here, if you divide 250 by 9, you get a little over 27. I think it's 27.7 repeating. And then if you divide 250 by 450, you get 55.5 repeating. So if we were to connect those two, right, so 55.5 repeating, a little over 27 right here, you're going to get the red inequality here, which is for the cost. So as long as we stay below this red line here, or on the red line, then we're good in terms of cost. All right? See, we have a y-intercept of 40 here, and or x-intercept of 40, and a y-intercept of 40 here. So this is the number of items. We don't want to purchase too many items. So as long as we're below this blue line or on the blue line, then we're good in terms of the number of items that we've purchased. Now, we want to satisfy both of those, right? We want to be under in terms of our cost, and we also want to be below or on 40 items that we've purchased. So this overlapping region right here is where that's going to satisfy both. So any points in here, and by the way, let's see, if we divide it by 4.5 to get that, that's going to be our X, which is food. Okay, so then this is food items here, food items, and then this one is the party favors. Okay. All right, so if we pick a point here, how about this one right here? This is the point 2010. So we can buy 20 food items and 10 party favors. Or we could purchase, this point is technically a solution, right? We could purchase 40 food items and no party favors. We could purchase something right in here to balance it out a little bit. Let's see, this can be 22, 4, and 14. So 24 food items and 14 party favors. Anything in here, in this region right here, over to there, up to there, and then from there up to there. Anything in that region or on this line or this line segment here are going to be solutions. So there's an infinite number of possibilities, right? But all of them are constrained in here. Actually, I'll take that back. There's not an infinite number of solutions if we only think about the context, right? Because we can't buy like a fraction of food items or decimal version of party favors or something like that. So there is actually a finite number of solutions here. All of these in here, and in fact, even the halves of those, because we're on a scale of 2 right now. So there's a lot of solutions, but there's not an infinite number of them. So I'll take that back. All right, so that's kind of how we do a system of linear inequalities. We graph the first inequality, shade above or below, make sure we are paying attention to whether it should be dotted or not. Then we graph the second inequality, again shading and paying attention to whether it's dotted or not. And then we find out where they overlap. And that overlapping region of our graph is the solution system to our system of inequalities. As opposed to systems of equations where we have one solution or no solution or an infinite if they're the same line. Now we're looking for maybe a two-dimensional region in which they overlap to be our solution to the systems of inequalities. All right, so hope that gives you an introduction to systems of linear inequalities, and hopefully you can build on that from there in solving real-world situations and problems involving those.